A very good morning to one and all. We sincerely apologize for the delay. So to begin today's proceedings, we have a talk on probabilistic models for machine learning by Adway Mitra. Adway is a Ph.D. student at the Department of Computer Science at the Indian Institute of Science. His research interests lie in the field of machine learning, such as Bayesian non-parametrics, topic models, and low-rank matrix recovery, and in the field of computer vision with topics such as video summarization and segmentation.
So I don't need this, right? Okay, so hello, can everyone hear me? Okay, so good morning everyone. As you heard, I am Adway, and today I am here to talk about probabilistic models for machine learning. Now I heard that many of you are interested in machine learning, and so no wonder we have got quite a few talks related to machine learning. We have already heard two talks, I guess, one an introductory talk and one about the more mathematical aspects. Now this is going to be the third aspect of third talk regarding machine learning, in which I am going to tell you about how probability or probabilistic models are used for the field of machine learning. So as you would have understood by now, that machine learning deals mostly about data. You have to collect the data and you have to represent it through mathematically, and with the aim of understanding or analyzing the data. And for this mathematical representation, different mathematical techniques are going to be required. So one of them is, for example, is linear algebra, which I guess yesterday you have learned a bit about. Another thing is probability. So why do we need linear algebra for machine learning? Mostly because, like, the data which you have, they are often represented in the forms of vectors and matrices. Now why do you need probability? The data which you will see in the real world, they have a lot of uncertainty in them. Like, for example, in yesterday's talk by Professor Sripati Arun, he was showing you all those images of, like, different animals and all those. So you saw that there are a particular animal itself can have variations in appearance or poses and various different kinds of deformations or variances. And this is in some sense some kind of uncertainty in the data, and probability is like one good and elegant mathematical tool to deal with these kinds of uncertainty. So in case of machine learning, what you will normally have is data. Say you have n data points, d1 through dn. These d1 through dn, they can be single numbers, or they can be vectors, or they can be matrices, or they can be something more complicated also. When you are doing machine learning from a probabilistic point of view, you are going to represent all the data as random variables. So if you have capital N data points, you will consider them as random variables, and you will assume that there is some probability distribution from which these random variables are coming. Now what exactly that distribution is going to be, that will again depend on the type of data. For example, if the data is something simple as you have a coin and you have tossed it n number of times, capital N times, and you have observed the outcomes. The outcomes are your data. So in this case, all the outcomes which you have will be a sequence of heads and tails basically. So only two values. You can look upon it through a boolean or a random variable which takes only two values, a binary variable. So what is a good probability distribution for these kinds of variables? You will have most of you will know that like the Bernoulli distribution is for this kinds of variables. If you have a Bernoulli distributed random variable that takes only two values, 0 and 1, say. and it takes maybe the value of 1 with probability p, and it takes the value of 0 with probability 1 minus p. So this p, that is something called a parameter. Now if the data is something like this, a sequence of heads and tails, basically a binary, if the data is like binary, then you will automatically know that the random, you are going to represent it as a Bernoulli random variable. But apart from that, there is the value p. Now what that value of p is going to be, that is something that you will have to estimate from the data, that you may not know a priori. Similarly, instead of a coin toss, suppose you have a dice with 6 faces, which is rolled some capital N number of times. So your data will be like some value between, every data point will be some value between 1 and 6. So so if you represent this as a random variable, it will be such a random variable which takes only 6 values, a discrete random variable which takes only 6 values. Now this you can represent like with a 6-dimensional multinomial distribution, and then it will have all these parameters, like with probability p1 it takes the value of 1, with probability p2 it takes the value of 2, and so on. And of course we know that if it is a distribution, if it is a probability mass function, all these p's must sum to 1. That is something we know, but what these individual p1, p2, p3 are, this we don't know, and this is something which we have to find out given our data. And similarly, if it is some if instead of discrete values, if the data is something continuous, like say some temperature readings, then obviously Bernoulli or multinomial is not going to do. In that case, you will need something like a Gaussian distribution or normal distribution, as most of you know about it. Again, you will also know that normal distribution or Gaussian, it has 2 parameters, the mean mu and the variance sigma. These also you will have to find out from the data, and how we are going to find that we are coming to, and that is what we call as parameter estimation. So this p or the p1 through p2, p1, p2, up to p6, or the mu and sigma, these are all parameters of the distribution which you are going to find from the data. Okay, consider a very simple case. It is like you have n tosses, of which capital N1 are heads and the remaining all are tails. Capital N minus capital N1 are all tails. So like this. Now first of all we make an assumption. We make an assumption that you have made all these capital N tosses, they are what we call independent and identically distributed. Now why do we say they are independent? I think like that's of course probabilistically speaking, independent, the word independent has a probabilistic meaning. 2 random variables A and B, they are said to be independent of each other. Most of you will be knowing it. When if A and B are 2 random variables and they are independent, then what can we say about probability of A and B? Anyone? Sorry? Huh? This is? Oh, I can do it manually. It's okay, I can do it manually. Yeah, so probability of if A and B are 2 random variables, then we can say that probability of A and the joint probability of A and B, probability of A comma B, we can write as probability of A times probability of B. So if capital D, for example, capital D is something, by capital, here you can see probability of capital D. By capital D I mean the collection of D1, D2 up to D of capital N, basically of all these random variables. And if they are independent, then we can write it in this form, in this product form, the product of all the individual probabilities. and the identical I said independent and identically distributed. The independent part takes care of this. And what do I mean by identically distributed? I mean that all of them follow the same distribution with the same parameter, and in this case that is Bernoulli of P. So D1 we can say follows Bernoulli of P, D2 follows Bernoulli of P, like that. So if D1 is a head, say I mean it takes the value of 1, then the probability that D1 equal to head, that is small p, and if D2 is a tail, then the probability of D2 being 0, that is 1 minus p, like this. So ultimately, because we have reduced it to this product form, and we know that there are n1 heads and n minus n1 tails, so we will have that the probability of the entire data is nothing but p to the power n1 times 1 minus p to the power n minus capital N minus n1. Is this clear to everyone? Okay, so this is the probability of the data under the parameter of p. There is another way of calling it. We can also call this as the likelihood of the parameter under the data d, which will so probability in your maths classes you will all have seen this notation of probability of some random variable. When we are talking about parameter estimation, instead we can write it as a likelihood of the parameter given the data, like this. Now as I said, from the data which you have, the data of the sequence of all these tosses, you will have to find this parameter p. Now how do I find this parameter p? The simplest possible thing to do is what they call as the maximum likelihood estimate. That is, find the p which just maximizes the probability of the data or the likelihood of the parameter given the data. So how do you find the value of p which maximizes this probability? Of course, all of you know that for this to do this you will have to differentiate this quantity with respect to p, equate it to 0, solve for p, then check the second derivative whether it's giving maxima or minima. You will always see that it is giving maxima, and after equating it to 0, the value of p which you will get is just as simple as n1 by n. So what does this mean? There are n1 heads in n tosses. So that means that the fraction of the tosses which resulted in a head, that is just that itself is your maximum likelihood estimate for the parameter p. Something as simple as that. But this is very clear intuitively also. If you are just given n tosses in which capital N1 are heads, then if capital N is large enough, then you will probably be inclined to say that it is head with probability of n1 by n, even without knowing all this mathematics. Similarly, instead of these Bernoulli random variables, you can suppose you have Gaussian random variables, as we saw in the case of temperature readings, if you have continuous values like this. So once again, because of that IID assumption, the data we will write in this product form, the probability of the individual random variables di, and because all of them are identically distributed as Gaussian with parameters mu and sigma, this we know is the PDF for the normal distribution. So the likelihood of all of your parameters mu and sigma will be like the product of all the things like this, and you can easily see that that is nothing but this. If you take the product like this, because these are in the data points xi, they are in the exponent, so this will become summation, and because this sigma you are multiplying it capital N number of times, for each one you will have sigma to the power n, and the root 2 pi part you can ignore as a constant. So this is your likelihood, this term is your likelihood, and now you will have to, for your maximum likelihood estimate, you will need to find the mu and sigma which are going to maximize this. So once again you go by differentiating. First you differentiate with respect to mu. It is very simple and it will come out to be just this thing, and this you can understand this is nothing but the average of the data, the mean of the data. All of you will you know what mean is. So it's nothing but the sample mean of the data. And similarly, you have got this. This is a maximum estimate or maximum likelihood estimate of your mu. Next, what do? You check the maximum likelihood of sigma. So you differentiate this quantity with respect to sigma. Again, equate it to 0 and standard things, and you will find that sigma, the maximum likelihood of sigma or sigma square rather, which is the variance, that comes out to be this thing. Okay, so far what in both the examples which we saw, what we are using to estimate all these parameters, what we are using is just we are using the data, nothing else. Now what happens is if you don't have enough data, that is in real world you may not have control over how much data you are getting. Whatever, when you are working in machine learning, you will possibly be getting the data from some external source, some data collecting agency or whatever, and then depending on the data which you have got, you will have to do your analysis. Now if it happens that you don't have enough data, you have very sparse amount of data, then you will have to alter your techniques accordingly. For example, let us we talked about the case of these tosses. So if you have 100 tosses and you observe that 60 of them are heads and 40 of them are tails, then you can possibly say that the probability of getting a head is 0.6 and probability of getting a tail is 0.4. Now if you have only one toss, you have a coin and you have the result of only one toss and it's a head, then based in that case your n, capital N is 1 and capital N1 number of heads, that is also 1. But in that case, if you have only one toss, then based on that you are not going to say that this is like the Scholle coin, because it was tossed only once and it gave a heads, so it must be the Scholle coin. That you are not going to say. Instead, if you have some more data, say if you have two tosses and both of them are heads, probably then also you are not going to say that it is the Scholle coin. If you have three heads, toss it 3 times, maybe 4 times, 5 times, then also you are only getting heads. Maybe in that case you will feel suspicious that something must be wrong with this. So what is what is happening is, like in this case, when you just have no data at all, you probably have some kind of prior belief about what the data is, or what the distribution is like. Like if I tell you that I have a coin, that you will probably think that it's a normal, very normal coin, where it is as likely to produce a head as it is likely to produce a tail. Then maybe when you are as you keep getting more and more data, then maybe your understanding of it will change. So this is known as the Bayesian theory. What we are talking about so far, that was what they call as the Frequentist statistics. Where the probability of a particular event is like considered as proportional to the frequency of that particular event. While in the case of the Bayesian statistics, it's modeled as you have some prior understanding, some prior beliefs about the probability of that event. Then based on what you see, based on the data which you are getting, your belief might change slowly over time. So what is the advantage of the Bayesian approach? It can work even if you have less amount of data. Of course, it will work only if your prior belief is approximately true. If you have some absurd prior belief, if for example in the case of a coin toss, if somebody, some unusual person for some reason thinks that coins are actually like the Scholle coins, which have both sides heads, then maybe his or her prior itself is wrong. Then that cannot be helped. But as long as you are starting with a reasonable prior, then even if you have some small amount of data, you can do a good job of your analysis of the data in future. That's the advantage of the Bayesian approach. On the other hand, the advantage of the frequentist approach is that you don't need any kind of prior belief. It is like completely objective and driven by what you actually see. So, so these are the advantages and disadvantages. So now I am going to, now the point of thing itself, let us see in case of a from a Bayesian point of view. Now this parameter p which we had, this we earlier estimated based on our data. Now in case of the Bayesian viewpoint, this parameter p, this also you will observe consider as a random variable. Like you already had all those random variables d1 through capital Dn. Now this p also you are going to consider as a random variable, and if it is a random variable, you will have to have some kind of probability distribution on it. Now that probability distribution on this parameter, that will call it as the prior distribution. Prior means like before, right? Some before in some sense. It's like the distribution which we have before seeing any data. So like we know that p is going to take a values only between 0 and 1. It can take any value, any real number between 0 and 1 it can take. So accordingly we will select a distribution which takes values only between 0 and 1, and beta is one such distribution. Beta distribution, how many of you know what is a beta distribution? Okay, no one. Never mind. Beta is a distribution which takes values between 0 and 1, and it has that also has parameters alpha and beta, just like Bernoulli has the parameter of p, or Gaussian has the parameters of mu and sigma. So beta is also has parameters alpha and beta, and these alpha and beta, which are like the parameters of the prior distribution, we will call these as the hyperparameters. Now these also we may have to estimate, or we may fix those also. But let us assume for the time being that for whatever reasons we know alpha and beta, and we model this parameter p as a random variable which is distributed as beta of alpha comma beta. Now if it is a random variable, you will know that random variable, if you have a random variable, you can define its expectation, and expectation of this p under the distribution beta is nothing but alpha by alpha plus beta. Okay, so now probability of p, this is called your prior, and probability of d given p, this is, we will call it as your data likelihood. Earlier you saw that under the parameter p, the probability of the data which we saw here, this thing. Now if it is one convention where I am going to follow is, if this is a parameter, then I will separate it from the random variables with a semicolon. But in this case, this p itself is a random variable. So in this case we will represent it as a conditional distribution. Like most of you will have seen in your probability classes in college what's a conditional distribution, and you will know that from the Bayesian rule, probability of p given d is proportional to probability of d given p times probability p. And what is the proportionality constant? Come on, you all also know Bayes rule, I am sure. So what is missing here? What is the term which I have dropped? Sorry? Probability of d, exactly. So probability of, it should be probability of p given d times probability of d is equal to this part. Now probability of d, it's like the d is what we have already observed, so it is constant. So that it is irrespective of p, it is constant, so we are treating it as a proportionality constant. Okay, so probability of d given p is your data likelihood, probability of p is your prior distribution, and we will call this part probability of p given d as your posterior distribution. Like so look at these two things. This is probability of p with nothing given. that is prior, and this is your probability of P given the data, that is after observe, what is the probability distribution of P after you have observed all the data, that is called your posterior. So prior means before, posterior means after. So what is the distribution of P after observing the data? So now you will have to choose your probability of the prior probability and the data likelihood in such a way that the probability of P given D, and as you see you are multiplying with these two things. Now what forms these distributions are going to take, that's in your hand, and how you are going to choose it, first of all you will have to choose it in a way that that actually models the situation well. That is, if you have if your data is like heads and tails only, then this thing will have to be your Bernoulli distribution. But apart from that, you will also have to keep in mind that the whole thing is mathematically tractable. That is, if you multiply one distribution with another distribution, it may not, the product may not necessarily give such a distribution which is like a common or recognized form of distribution. That will happen only in some special cases. Like for example, if that is, we said that the prior distribution on P, we called it as the beta, as a beta distribution with some parameters. The posterior distribution of P after observing the data, it will be nice if that is also a beta distribution, maybe with other parameters. So it turns out that there are some distributions, that is, if the prior is follows some distribution D1, and if the data likelihood follows another distribution D2, then the posterior will again be the distribution D1. If there are some pairs of distribution D1 and D2 like that, and if such pairs we will call as like conjugate pairs, or in other, so for example, if the prior is a beta distribution and your likelihood is like a Bernoulli distribution, then it turns out that the posterior will again be a beta distribution, which is probably what you want. That is, your prior is like it's like probability of P, your posterior is also a distribution on P, so you should want them to have the same distribution. So if that prior is beta, then this property is satisfied. Similarly, if in the other case of Gaussian, in case of mu and sigma, if on the mean mu, if you fix the Gaussian distribution as the prior, and if your data likelihood that is also a Gaussian, then it will turn out that even your posterior posterior distribution on mu, that's also going to be Gaussian distributed. So it turns out that if you have if your prior distribution on P, if that is a beta of alpha comma beta, and then after that you observe your data points, so with capital N heads and capital N minus capital N1 tails, then what happens is your posterior distribution is again beta with the values like this. So your alpha, this is it was earlier this was alpha, now this has become alpha plus N1. Earlier this was beta, this has become beta plus N1 minus N2. So this is like the number of heads, and this is like the number of tails. So what has happened is, earlier you thought that your coin is distributed as beta, as some beta distribution. You still think so, but only the parameters which you knew earlier thought, now those parameters have changed a bit, and they are influenced by the data which you have observed. And earlier I told you that the expected value of P, that was like this, alpha by alpha plus beta. Now it has become alpha plus N1 by alpha plus beta plus N. So earlier what you expected the P to be, the bias of the coin to be, that also has changed after observing the data. And note that if earlier you had just thought if alpha and beta were both 0, then that is if you had no prior beliefs at all, then in that case what you will get is again N1 by N, which is the same as the maximum likelihood estimate. So this is what you call as the Bayesian estimate, the expectation of the posterior. and what it means is like your belief has got refined after seeing the data. Okay. So far we have been dealing with random variables. I told you right in the beginning that the data points which we are going to observe, D1 through D capital N, we are going to consider those as random variables. Then I initially told you that the P we will consider it as some parameter. It's like a fixed quantity which we don't know and which we are going to estimate from the data. After coming to the Bayesian part, I asked you to consider even P as a random variable which has some distribution attached to it. Now there is a difference between the data random variables D1 through D capital N and the parameter random variables P or maybe mu or sigma in the case of Gaussians. That difference is that for the D1 through Dn you are actually observing the values, you know what they are. But in case of these things like P, mu or sigma, these are not things which you are observing. They are like you in your mind or in your mathematical model they are there, but you don't know what they are. And it is so these things which we will call as latent variables. While D1 through Dn, these are, we can look upon them as observed variables. Now these latent variables, you will want to find out what these latent variables are. Just like in the Bayesian inference Bayesian case, we were trying to find a posterior distribution on the parameter on that P thing. We'll try, in general, if there are latent variables, we will try to find out something about them, and that process is known as inference in the language of probability. And when we are trying to find that latent variable, you will usually not get a fixed number. Instead, you will get a distribution. You will get a conditional distribution which is conditioned on the data which you have observed. So just like in case of your Bayesian estimate of the P, what we got in the was this thing, the posterior distribution beta of alpha plus n1. So this is nothing but a distribution. This is not a single point, it's a distribution on P, which we call as the posterior distribution. And in case of in your inference problem, you will typically be for whenever you have a latent variable, your aim will be to come up with some kind of a conditional distribution for those latent variables. I will show you that above. But once you have got this kind of distribution, then using the distribution you may want to find some kind of point estimate, like a single number. Now if you have a distribution, there are many ways to find a point estimate by that, like expectation of that distribution or maybe the mode of the distribution. Mode meaning the place, the value for which that the PMF or PDF or whatever is maximized. So if you are taking the mean of the posterior, then we will call it as the Bayesian estimate. If you are taking the mode of the posterior, then we will call it the maximum a posteriori estimate or the map estimate. Okay. So now we come to what is known as a generative model. We'll try. So what I have been telling you right now, I have been telling you something like you have data D1 through capital Dn, and then what we are thinking is we are considering a probability distribution from which these values, these random variables have come or have been generated, so to say. So this process, I am describing you a process in which these random variables have been generated. Like if you have capital N number of process, then I am telling you that there is some P and there is a Bernoulli distribution, and your D1 through Dn are all coming from that distribution. They are being sampled from the distribution of Bernoulli P. So in some sense I am giving you an idea of how the data was generated. So generative model is something which actually specifies the joint distribution of your data, and this joint distribution again is can factorize. Now I already have told you, like if A and B are two random variables, and if they are independent, then probability of A and B is like the product of probability of A and B. If instead of two variables, if you had capital N variables, then also you could factorize like this, provided they are, all of them are independent. So similarly, if it happens that some of them are independent but not all the others, then you will be able to factorize all the joint distribution of all the variables into some products. In each product, that is, it will involve a subset of the random variables. They may not be independent among themselves, but if you consider two different terms of the product, then the random variables coming in the two terms, they will be independent. And it is when you are a generative model specifies the joint distribution through these independencies or through the factorizations. And I have told you have seen about these prior distributions. So we will assume that all the latent variables or all the variables for that matter, they will have some kind of prior distributions, and there can also be some kind of conditionals. Typically we will have conditionals in the form of the observed variables conditioned on the latent variables, and your inference problem which is to find each of the latent variables like the p's, the mu's or the sigma, that inference problem is to find a posterior distribution Li given all the observed variables for each of the latent variables Li. So if you have only one latent variable p, your inference problem is the probability of p given your data. If you in the case of the Gaussian case, you have two latent variables, mu and sigma. So in that case, your inference problem requires two posterior distributions: probability of mu given your observations, and probability of sigma given the observations. And the challenge is to come up with those probability distributions, with those posterior distributions, and once you have come up with them, then you can compute its expectation or your mode or whatever we talked about. Like let me give you an example. So suppose there are three random variables A, B and C. Now I tell you a joint distribution, the generative model, the generative process will tell you that A is distributed as normal between 0 with parameters 0 and 1, a standard normal Gaussian as you will have learnt in your school or high school or college. So in this way A is coming, and there is another random variable B which is distributed as also distributed as normal with parameters with mean 5 and your standard deviation 0.5. And I tell you that there is a third one C which is distributed with a mean of A plus B and standard deviation of 0.5. So C in some sense it depends on A and B. So A and B are independent, but C is dependent on A and B. So this joint distribution A, B and C, this factorizes in this way. That is, you can write it as probability of A times probability of B times probability of C given A comma B. And now if I tell you that A and B are latent, or you don't know A and B but you have observed C, in that case what we need to find out is our inference problem is going to be to find posterior distributions on both A and B, because they are latent variables. You will need to find them through inference, and for that you need posterior distributions. So these are the two posterior distributions you will be looking to find. How we will get them is a different story, and for that you will have to make use of these the exact forms of the distribution, and you will have to compute the conditional, do some algebra and come up with it. Okay, so another I will also tell you something about you will have heard the term classification in at least two of the talks so far. So in case of classification, what happens is you have your data. Each data is represented as something like a d-dimensional vector maybe, or something more complicated, and each data point, it has a class level. It can be binary classification in which there are only two possible class levels, or it can be a general case of classification where there are k levels. For example, if you like, you can think of image classification. For example, the question may be something like you are given images of lots of images, and you are being asked, is this the image of a human being or is it not an image of a human being? That is like a binary classification problem in which there are two categories, human being and non-human being. Or similarly, there can be multi-class classification. You might be given an image and you may be asked to categorize it as either a human being or a car or an aeroplane or a mango or a tree. So this is a 5-class classification. So mathematically we represent it like this, that there is a feature space in d-dimensional vectors basically, and this y, the calligraphic y, that takes that is, we will call it as the label space, that is like a discrete variable which takes one value between 1 and capital C, where capital C is some positive integer. And a classifier is a function which maps a feature vector in this d-dimensional space to one of these capital C integers. That's called your classifier. Now, in case of a generative model of classification, say we'll define these kinds of conditional distributions, like the conditional distribution of the feature vector provided the class label is k. So, for example, if you are in the image classification example which I was talking about, say suppose your feature vector is something like the average intensity or average pixel color of in the image. So if it is a human being, then you will expect its color to be something more towards the flesh color, whatever that is in case of whatever its pixel value is. On the other hand, if it is a tree, then it will be closer to green. So, the distribution of the feature vector, that is in some sense conditioned on the class level itself. So, this probability of x conditioned on the class level is like a class specific distribution on the feature vectors. And this x, we have said it's a d-dimensional vector. We can, there is, in case of naive based classifier, we make an assumption which may often be wrong. The assumption is that all these d dimensions, they are independent of one another. And we have already said many times that if the random variables are independent, then they are joint distribution that can be written as the product of the individuals. So the probability of this is like a joint. This x means is nothing but x1 through xd, and this we write in this factorized form. And how do you do classification? Classification is again this again turns out as the finding out the posterior. So in this case, x is going to be your observed variables, and y, the class level, that is your latent variable which you need to find out. And again, because we are considering a Bayesian setting, we will not find an exact class level. Instead, you will find a distribution, or as we call it as the posterior distribution of y. And your classification is this thing only, the posterior probability of the class level k of the class level y given the feature vectors x, and that you know by Bayes rule is nothing proportional to this thing, probability of x given y equal to k, and this is your class specific distribution, and this is your prior distribution on the classes. So why is this important? Now suppose for some reason, whatever reasons, you have reason to believe that there are many more human images than tree images. So that is some kind of prior bias you have, that if you are given a random, if you somehow know that there are many more human images than tree images, then you will probability that y, the class level is human, that is you can think it is higher than the probability that y is equal to tree, even without observing the data. And once you have observed the data, your valuation or your belief will change, and that is captured through the posterior. So this is classification through the Bayesian point of view. Okay, we have, I think, only about 15 minutes left, right? Huh? 10 minutes. Okay, I will not go into this. Instead, I will show you something more interesting. Okay, condition. I have told you. We have already talked about independence. So two variables, random variables A and B, they are. We say that they are independent if probability of the joint distribution A and B factorizes as probability of probability of A times probability of B. Now, I am going to tell you something which we call as conditional independence. What do I mean by that? So, you are all familiar with these kinds of terms, like the conditionals. So, we will say that if there are three random variables A, B and C, if I know C and under the knowledge of C I can say that A and B are independent, then we will say that A and B are independent conditioned on C, and we write it in this way: probability of A comma B conditioned on C, that factorizes as probability of A conditioned on C times probability of B conditioned C. I will show you an example. Say for example, A is like distributed as mu comma sigma square, a normal, some kind of normal. Then C, that is distributed as A comma sigma square. And finally, B is distributed as Gaussian with mean C and again variance sigma square. So what happens to the probability of A and the joint probability of A and B conditioned on C, right? So we can write these as the joint divided by probability of C. This all of you know, right? All of you will know this step. Now there is something called chain rule of probability. If there are more than two random variables, we can decompose it as products in this way. We will write it as probability of A, then we will write it as probability of C given A, then we will write it as probability of B given C comma A. If there are more things, say D, then after this we will add probability of B given A comma B comma C. So so this is something which we call as chain rule of probability. So next, this we concentrate only on this part: probability of A times probability of C given A by probability of C. Now all of you will know that this is nothing but probability of A given C. So these two terms come down to probability of A given C, and now we focus on probability of B given C comma A. Now for this you look at the distribution of B like this. This says mean C and sigma square. Now this, as you will see, C is, we are saying that C is observed. We know what the value of C is. So effectively its mean is known and its variance is also known. So here A is not playing any role in the distribution of B. So this there is no point in having A here. This is not giving you, since you know C, this is not this having A is not giving you any advantage. So we just drop this. So what we have is probability of B given C. So this probability of A comma B given C, this factorizes in this way: probability of A given C and times probability of B given C. So so this is like what we, in this case we will say that A and B are conditionally independent given C. Okay, now we'll talk about something new called the graphical models. Now graph theory all of you are quite familiar with, so all of you know about graphs. So graphical model is something that has been described by mathematicians as a marriage between graph theory and probability theory. So this graphical model, this is one elegant way of representing elegantly representing all the joint distributions, their independences, their factorizations and all that. So what is, so if you will consider, in case of graphical models, you are going to consider a graph. What kind of graph? Now, a graph in which each node represents a random variables, and between the different random variables there may or may not be edges. If between two random variables there are no edges, then you can say they are conditionally independent. Conditionally independent, conditioned on what? So conditioned on everything else, or maybe a subset of the remaining things. So there again, as you know, there are two kinds of graphs, directed and undirected. So in case of, we'll consider the two cases one after another. In case of directed graphs, it's like there's a fancy name for directed graphical models, Bayesian networks, and in case of undirected graphical models, they are known as Markov networks. I will tell you about both the things. How much time? 5. Okay, Bayesian networks. So in this case, it's a directed acyclic graph. So many of you will be knowing about DAGs or directed acyclic graphs. You know that if there is a directed acyclic graph, then you can do something called a topological sort on it. So all of you know about topological sort, I guess. So if you do a topology, this kind of topological sort, you can represent it as you can have these parent-child relations on that. So you can each edge, like I have said that each variable or each node of the graph represents a random variable. So each edge is going to signify a distribution like probability of x given its parents x. Something like this. Like there is an arrow between A and B and an arrow between B and C. So in this case, the A, B and C are three random variables. The parent A is the root variable, it has no parents. For B, it has one parent A, and C has one parent B. So the distributions, each of these edges are going to have a distribution which is like probability of B conditioned on A or probability of C conditioned on B. So the entire distribution, the joint distribution of all the variables x1 through xn, this again factorizes in this form. It factorizes where each factor is like stands for one edge. So I equal for each of the random variables xi, we can write it in this form. Probability of xi conditioned on its parents of xi. And so what's the great thing or what's the best thing about the graphical model? It helps you to represent the conditional dependencies or independences in a very elegant way. For example, this A, B, C, this is like very similar to the example which I just gave you, where A is like a normal with some mean and variance, B is normal with mean A, and C is a normal with mean as B. So the first one is like that, and in that case the conditional independence as I told you, it can be factorized in the form of probability of xi conditioned on its parents. So in this case, the joint distribution of A, B and C, that can factorize in this way. Probability of A times probability, that's the root node, so we will just have a probability of A turns on that. Next, for the next edge, it is we have probability of B given conditioned on A. So the B probability of B conditioned on the parents of B, and parent of B is A. So the second term is probability of B given A. The third term is probability of C given parent of C. And what is the parent of C? B. So we will write as probability of C given B. So this is its the factorization of this distribution. Similarly, if we can consider another graphical model like this, in which the arrows are from C to A and C to B. So in this case, the root node, what is the root node? C is the root node. It has no parents. So we will start with probability of C. And after that, what else is there? We have for A, what is the parent of A? C. Yes, there is one arrow from there. So we will write probability of A given parent of A, namely probability of A given C. Probability of B given parent of B, probability of C. And it turns out that in the previous case it turned out that we already derived that. We derived that probability, in that case A and C are conditionally independent given B. It turns out that in this case A and B are conditionally independent given C. And a third, this is a third example of a Bayesian network where we have A and we have B and they are combining to generate C. So in this case we will have probability of A, probability of B, both of them can be considered root nodes, and then we have probability of C conditioned on parents of C, and A and B in this case are both parents of C. So C conditioned on A and B. Now the question is, in that case conditioned on the central variable, we could say that the side variables are conditionally independent, we saw. But in this particular case it turns out that we can't make any statement like that. That is, even if C is observed, then we cannot say that A and B are conditionally independent. That is, it tells us, I mean, if C is observed, then if we then A and B are actually related in some sense, and we are not able to say that they are conditionally independent. This is a more interesting example. So this is about for a student. So maybe there is a student writing an exam. So there can be something, there is one variable called the difficulty level of that exam. So let's naively assume that it has two difficulty levels. The exam can be either easy or difficult. It can be easy with probability 0.6 or it can be difficult with probability 0.4. So this is a binary random variable for the examination which the student is writing. And next is about the intelligence or talent of the student. The student can be intelligent with a student can have two levels of intelligence. Either she can be very intelligent or she can be an average student. She can be very intelligent with probability 0.3 or she can be an average with probability 0.7. Now what grade that student is going to get in the exam, that way is going to depend on both her intelligence and the difficulty of the question paper. So this is a more complicated distribution. So that's why we depend. So if it is if it is easy and if she is not so intelligent, then she can get a she can get a good grade with probability 0.3, an average grade with probability 0.4, and a high grade, a bad grade with probability 0.3. Similarly, if she is not that intelligent, means if it is easy, if intelligence takes the value 0, and it's a very difficult exam, then she is likely to get a bad grade, and like that. So the grade depends on both the difficulty level and the intelligence. And then there is this thing about recommendation letter, and the recommendation letter which she is whether she will get a recommendation letter from her professor or not, that will depend on the grade. It can depend on some other things also, but let's assume for the time being, a naive assumption may be that it depends only on her grade in such and such way. That is, if she gets a good grade, then she is more likely to get a good recommendation letter. If she gets a bad grade, she is less likely to get a good recommendation letter, and things like that. So this is one practical example of a Bayesian network. Remember that we are only showing you how to represent the information as a Bayesian network. I have not yet said what we do once we have the Bayesian network. That I will come to later. Okay, so we saw that in case of Bayesian network, each of the joint distribution factorizes in the form of probability of a random variable conditioned on its parents. So if the data or if the system which you have that can has a natural interpretation in this parent-child relationship, then we will try to model it through a Bayesian network, just like we saw that student example. But it may happen in some cases that it's not very easy to write those conditionals. That is, the system may not allow you to give an elegant way to consider these parent-child relationships between the different factors. Rather, it might be simpler to consider a collection of random variables at a time. And in these cases, what you have is a Markov random field or an undirected graphical model. So, since this is a graph, it's going to have clicks. What is a click in a graph? Anyone? What is a click in a graph? Okay, a click is a maximal is like a complete subgraph, a set of the vertices where every pair has edges between them. So in this case, the joint distribution of the random variable we write as a product of click functions. For each click, or rather maximal click, for example, by maximal click I mean a click which is complete, where every pair of vertices in that subgraph has an edge between them. But if you try to add any new vertex, then that property is wasted, is gone. So it's a maximal click, and you can write the joint as a product of these click functions, which we'll call as click potentials. An example, for example, again A, B and C, for example, so in this case there are only two maximal clicks, AB and BC. Two very like the simplest possible click, the simplest clicks with only one edge between them. So in this case we are going to write it as the click potential of AB times the click potential of BC. In a more complicated example, there are in this case there are 4 random variables, and the click is like this. This is one click with 3 variables, and there is a third one. One last slide. So in this case you can factorize it in this way, as a click potential of the big click ABC and of the small one CD. And an application of this where we see this is like one nice example may be image denoising of a binary image. A binary image like in which each pixel takes the value either 0 or 1 or 0 to 55 if you want to call it. So suppose in the true image each pixel takes a random variable, you consider each pixel as a random variable, and in the true image it takes the random variables as x1 through xn. In the noisy image, in which each of those pixels are flipped at random or is flipped with some probability. I mean if there is a black pixel, then with some low probability we will convert it into a white pixel. If there is a white pixel, with some probability we will convert it into a black pixel. So this is a noisy image. And there is one property in images, that is they are basically smooth. That is, smooth means two adjacent pixels are likely to be like equal with very high probability. Like if you consider two pixels side by side within the banana, then like they are going to be both of them are going to be white. If they are outside, then both of them are going to be black. There are only very few pixels at the edges where they are not equal. But the probability of if you take two pixels or two neighboring pixels at random anywhere in this image with very high probability, they are going to be, both of them will be black or both of them will be white. And it is this property which allows us to think in terms of pairs. Now, like instead of thinking in sequences as we were thinking in the instead of the causality relation which we saw in the student network, we will think of as pairwise relations. And so we will define the probability, the joint probability of two pixels in this way. That is, it's like its probability is high if both of them have the same values, and it will be low otherwise. And so so we saw examples of two graphical models, and now what do we do with these graphical models? One is inference. That is, inference, as I told you, as the latent, as distributions on the posteriors, or posterior distribution on the latent variables. And for we can make use of graph algorithms to come up with these things. with those posterior distributions. Another thing is like the parameter estimation, which I already told you. Like for example, in the case of Bayesian networks, you have these age distributions, and for that you need to estimate the parameters. Or there can be structure learning, where you structure learning means there are random variables and there are ages. Now between two random variables, will there be an age or not? That question is known as structure learning. So that is also one problem which you need to do on graphs. So there are some more things which I would like to tell you, but for the lack of time I will stop here.
Yeah, we are running a bit late, so thank you Adway for the talk. I think I'll skip the